Hello students, today we are going to discuss the chemical properties of aryl halides. Welcome to your favorite channel Science with Mukherjee sir, myself KK Mukherjee. Today we are going to discuss the chemical properties of aryl halides. So let us have the headings of today's video is this is the video number 11 of this haloalkanes and halogens. Already in our previous video, we have discussed about the chemical properties of the alkyl halides. The chemical properties of the aryl halides can have the three dimensions. The three dimensions are, you can say, first one, that is nucleophilic substitution reaction. Nucleophilic substitution reaction. Second, that is the electrophilic substitution reaction. Electrophilic substitution reaction, and third, the reaction with metal. The third portion we have already covered in our previous video, that is video number 10, that we have observed how the aryl halides going to react with the metals. Okay. In this today's video, we are going to discuss the nucleophilic substitution reaction. If we see one thing that is clear to us, that we can write also that the chemical property, the chemical reactivity of aryl halides is very less as compared to the alkyl halides. So make a underline of this statement. This is a very important statement. That is, chemical reactivity of the aryl halides is very less as compared to the alkyl halides. Why it is so? That we are going to discuss now. There are basically three reasons that you will get. Number one, that is the resonance effect. Number one, that is the resonance effect. Number two, that is the hybridization of carbon. This is sp2. Hybridization of carbon in case of aryl halides, it is sp2 hybridized. And number three, the repulsive effect. So there is three reasons that are going to contribute to the chemical property of the aryl halides, which is found to be very less as compared to the alkyl halides. That is three reasons. That is number one, that is the resonance effect. Number two, that is hybridization of carbon in the aryl halides. Number three, that is the repulsive effect. So let us understand first, that is the most important thing, that is the resonance effect. First we are going to understand the resonance effect. Resonance effect. The lone pair electrons in the halogen do in conjugation with the pi electrons of the benzene ring, and they will make some hybridizing structure. And this structure, from this structure you will be able to understand that there is a double bond between the carbon and the halogen. So the structure is like this. You can see this is the aryl halides, the halogens, and there is a lone pair electrons you can see in the halogen atom, and this will make a resonance effect, and there is a different resonating structure will be observed. So you can see that is a resonating structure of this alkyl aryl halides. You can see the lone pair electrons has been in conjugation with the pi electrons of the benzene ring, and there is eventually a double bond is formed between the carbon and the halogen. And when this double bond is formed, means that you have to break this double bond for carrying out the nucleophilic substitution reaction. For the alkyl halides, this type of double bond is not there. So what is going to happen? You need a drastic condition to carry out the nucleophilic substitution reaction in case of aryl halides, and that is the most important reason for why the nucleophilic substitution reaction in regard to this reaction, the aryl halides is not much responsive, not much very reactive towards this. Number one, and number two, and another thing that you understand, in the alkyl halides, the bond length of CH bond length is 177 picometer, while in CX bond, in case of this is alkyl halide, and the CX bond, that is a double bond character, you will find the bond length is 169 pm. So what is required? There is a greater energy is required for this nucleophilic substitution reaction, because for when you go for undergoing the nucleophilic substitution reaction, you have to break this bond, and until unless you are not able to break this bond, you are not able to carry out this reaction. So that is one of the main reasons. And second reason you can say, that is the hybridization, sp2. The carbon atom in the aryl halides is sp2 hybridized as compared to the alkyl halides. So you can write this in this way. This is sp2 hybridized, and in case of alkyl halides, suppose this is sp3 hybridized, and due to this difference in hybridization of this carbon atom of the alkyl halides and aryl halides, what we will find, there is the difference in the bond polarity. The bond polarity is higher in case of alkyl halides, higher in case of alkyl halides, as compared to your aryl halides. That is the one of the reasons. And last reason, that is the repulsive impact, because you see the benzene ring itself is an electron rich. There is a lot of pi electrons in the benzene ring is there. So nucleophile is also a electron rich species. So there will be the repulsive interaction between these species. So it will not going to undergo the nucleophilic substitution reaction very easily. It requires some drastic conditions. So we will now understand what drastic condition do you need to carry out this nucleophilic substitution reaction. Okay. So you can see there is some typical reaction of the nucleophilic substitution reaction by the aryl halides as given here. Here is a chlorobenzene in presence of the 48% NOH and with a 300 atmospheric pressure and temperature 623 Kelvin. It will fast sodium phenoxide, it will fast with sodium phenoxide, then with the presence of the dilute HCl it will give the phenol, and this is called the Dawes process. This is called Dawes process. Second example reaction you can see from the chlorobenzene with the help of the ammonia and CO2 with the strict condition that we have to create 600 atmospheric pressure with 475 Kelvin, and you will get the aniline. This is also another example of the nucleophilic substitution reaction by the aryl halides. Here bromobenzene you can see with the help of CuCN and pyridine has been taken, and this will create the benzonitrile. And all those reaction is being carried out under a very dusty conditions. Now the mechanism of the reaction, there are basically, as you can see, in case of alkyl halides, there is basically two reaction mechanism that you can see, that is SN1 and SN2 that we have discussed in our previous videos. The reaction of this nucleophilic substitution is normally being carried out in different mechanisms. There are two mechanisms there. First mechanism that we are going to discuss, that is mechanism of nucleophilic substitution, that is first one bimolecular in this bimolecular first addition and then elimination. In the addition step, carbon, the production of carbocation. And this carbocation that you will now understand, this is chlorobenzene, and OH is a nucleophile. The intermediate is formed here. And these intermediates here, this carbocation is stabilized by resonance. The OH has been attracted to this halogen, to this carbon atom where the halogen has been incorporated, and it will create a carboanion, and this carboanion is stabilized by this carboanion is stabilized by this resonance effect. And this is a very slow process, and you can say it is a rate determinant process. In the next step, what is going to happen in the next step? The chlorine will depart, the chlorine will depart and the formation of the phenol. So there is two steps. In the first step, you see there is addition of OH, hydroxyl ion. In the second step, there is elimination of this halogen. So this is the two steps by which you can able to see the production of the nucleophilic substitution reactions. And now this carboanion can be stabilized by the use of the different types of groups. Suppose in the carboanion, this is a one carboanion, suppose. And another carboanion where there is this nitro group is at the para position. And another carboanion where the methoxy group, which is basically we can say the anisole, OCH3 group, this is the 3 carboanion, and these 3 carboanion you can see the number 2 carboanion, these carboanion, that is para nitro chlorobenzene, para nitro chlorobenzene, you can see it will be much more stabilized carboanion as compared both these two, because here this is an electron withdrawing group, and this electron withdrawing group will discharge the minus charge from here, minus charge from here, and it will be much more stabilized as compared to this carboanion and also to this carboanion. And in this case you can see this is much less stabilized than this, because it will have the plus I effect, that it will electron releasing effect, and this will make the electrons will be concentrated at that point only. So this carboanion will be highly stabilized. So in that case, when you are going to do the nucleophilic substitution reaction, if there is an electron withdrawing group on ortho and para position, the reaction will continue, reaction will carry out with very easily, and with less drastic condition you need it. This condition that what we have said, that you have some atmospheric pressure, you need some temperature, specific temperature. This condition is gradually reduced. For this 2,4,6 dinitrochlorobenzene, only one from the one water you can able to produce this phenol. So that is all for today's video. In the next video, what we are going to understand the next, that is reaction, that is electrophilic substitution reaction, we will discuss. And if you like this video, if you can share to your friends, and I am totally 100% sure that you will be benefited out of that. So all the best for this video. Thank you very much for the listening. All the best.